Welcome to The Explainer. You know, in chemistry, you spend a lot of time learning the rules. But what happens when a reaction seems to, well, break them? Today, we're going to solve a classic chemical mystery. Why a simple reaction can sometimes give you a product you absolutely never expected. Okay, so let's dive right into the puzzle. In organic chemistry, you learn all these awesome rules to predict what's going to happen when you mix stuff together. But every so often, you run into a situation where the molecules just do their own thing. So imagine this. You set up a reaction. You're expecting a pretty straightforward swap of one chemical group for another. Simple, right? But then you run your analysis and you find this other thing. A totally different product where it looks like a hydrogen atom has just, packed its bags and moved across the molecule all by itself. What is going on here? To crack this case, we have to get back to basics. The kind of reaction we're dealing with here is called a substitution. And honestly, it's just what it sounds like. One group comes in and another group leaves. It's a swap. But as we're about to see, how that swap goes down, well, that changes everything. And to really get a handle on this, we're going to use let's call it a memorable analogy. Let's imagine two cats and one very, very comfy chair. Believe it or not, this little drama perfectly explains the two major ways these reactions can happen. So our cat, our molecule, has a choice to make. Option one is the patient approach. Just wait for the other guy to leave. This happens in multiple steps. Option two is the aggressive approach. Just go in and kick him out. This happens all at once. The real difference here is the timing. Okay, so let's swap out our feline friends for some actual chemistry terms. Cat number one, the newcomer who wants the chair, that's our nucleophile. Cat number two, the one already in the chair, that's our leaving group. And that super comfy chair that everyone wants, that's the carbon atom right at the center of all the action. All right, first up, the aggressive strategy, the get out of my chair now approach. In chemistry, we call this the SN2 reaction. That little 2 is super important. It means that two things, the main molecule and the attacker, are involved in the single most important step. With the SN2 path, there is zero waiting around. It all happens in one smooth, coordinated move. We call it a concerted step. The attacker, our nucleophile, comes in from the back, and at the very same moment, it boots the leaving group out the front. Bam! It's this beautiful, efficient, one-step chemical dance. Now, here's the thing you have to remember about SN2. It hates crowds. Hates them. If that central carbon atom has a bunch of bulky groups attached to it, what we call steric hindrance, the attacker just can't get in. And because it has to attack from the back, it causes the whole molecule to flip its 3D shape, kind of like an umbrella turning inside out in a strong wind. Okay, so that was the forceful way. But what about the other option, the patient wait-and-see approach? This is the SN1 reaction, and that one tells us that only one molecule, the main one, is involved in the slow, rate-determining step. The SN1 path is a completely different ballgame. It's a two-step process. First, and this is the slow part, the leaving group just leaves. It takes off on its own. This creates a temporary, super unstable middleman, an intermediate. Then, in a much faster second step, the new group comes in and attacks. And that intermediate? Well, that's the key to our whole mystery. So this intermediate is called a carbocation. Basically, it's a carbon atom with a positive charge, which makes it incredibly reactive and unstable. It's desperate to react with something. And this needy, unstable little guy, this is the culprit behind our original chemical puzzle. So the whole game with SN1 is about forming the most stable carbocation you possibly can. And because this carbocation is flat, the nucleophile can attack it from the front or the back. It doesn't care. This means you often end up with a mix of products, totally scrambling the original 3D shape of the molecule. All right, let's recap. We have our two pathways, the one-step SN2 and the two-step SN1. We have our prime suspect, that unstable carbocation intermediate from the SN1 path. With these clues, it's finally time to go back to our mystery and solve this thing once and for all. And here is the crucial clue. See, not all carbocations are created equal. Their stability totally depends on how many other carbon groups are attached to them. A tertiary one hooked up to 3 other carbons is the most stable. It's the king. A primary one, on the other hand, is super unstable and really hard to form. So, back to our mystery reaction. The leaving group decides to take off following that SN1 pathway. And when it does, it creates a secondary carbocation. Now, secondary it's okay. It's stable enough to exist for a moment, but it's not the most stable it could possibly be. It's like sitting in a decent chair when you see a plush, super comfy recliner right next to you. That unstable carbocation has a split second, a tiny window of time before it gets attacked. And in that moment, it does something absolutely remarkable to get to that comfier chair. It rearranges itself in a process we call a 1-2 hydride shift.
Now, this might sound a little weird, but the motivation is dead serious. It's all about finding more stability. What happens is a hydrogen atom on the carbon right next door, along with its 2 electrons, just hops over to the positively charged carbon. It's a tiny little internal jump, but it changes everything.
And boom, that little hydride shift instantly turns the so-so secondary carbocation into a much, much more stable tertiary one. And it's this new, rearranged intermediate that our nucleophile finally attacks. And that is why we get the unexpected product. The molecule literally fixed itself to get into a more stable state before the reaction could finish. Mystery solved. So let's put it all together in a final side-by-side comparison. Because understanding the key differences between SN1 and SN2 is really the secret to knowing when a reaction is going to be simple or when you have to watch out for these clever little molecular rearrangements. This table right here, this is your ultimate cheat sheet. You can see the preferences are basically opposites. SN1 loves crowded carbons because they form those stable carbocations. SN2 needs wide open space to get in and do its thing. And look at that last row, rearrangement. It's a signature move of the SN1 pathway, but it's completely impossible in an SN2 reaction. That's our answer in a nutshell. So the big takeaway here is that molecules are, well, they're restless. Just like everything else in nature, they are always looking for a state of lower energy and greater stability. That fundamental drive is the entire reason for these rearrangements, and understanding it helps us predict even the weirdest chemical behaviors. It's a great reminder that in chemistry, there's always a fascinating story happening just below the surface.